was already done. Then we did positional isomerism. So in positional isomerism, we changed the position of the functional group. In chain isomerism, we changed the carbon length of the compound. And we are now doing the third one, which is called functional isomerism. So let's have a look at what happens in functional isomerism. So as the name suggests, when it comes to functional isomerism, the isomers have same molecular formula. They have the same molecular formula, but different functional groups. So now the functional group itself is going to change. Okay, so there are two major group of compounds what we have to consider. In fact, three of them, but let's have a look at the first two. So for example, this is A. Okay, I'm switching between aldehydes and ketones. See, this is very fast way of understanding the whole thing. The switch is between aldehyde and ketone, and the reason why we do that, because they both have same general formula. They both have same general formula. Do you remember what is the general formula of this one? Anyone remembers? You could write it in the Zoom chat. That's correct. So, oh, sorry, just a second. So the general formula you said was CnH2nO. So that was a general formula, correct? Now, what I'm going to do is, I'm going to give you one example first. I'll give you molecular formula, and the challenge for you guys would be to make a aldehyde and make a ketone out of it. Just to refresh memories, aldehyde, they look like this, RCOH, and ketone, they look like this. And you must also now remember how do we name them. So aldehydes, if you remember, they are named as alkane L, and ketones are named as alkane dash on. But don't forget, the position of the ketone is from 5th carbon onwards. So this is the position of C double bond O, that's the ketone, from N equals to 5 onwards. Okay, so let's have a look at some examples of aldehyde and some examples of ketone under the same molecular formula. So if you're ready, we'll go to our next page. Could you just type R for ready so I know that I can go to the next page? You will be getting the PDF of this once I finish the class here. Okay, ready? Can I go to the next page? So I'll give you a molecular formula, and your job is to make an aldehyde out of it and make a ketone. And if you can make more than one aldehyde or more than one ketone, please go ahead and do it. Okay, let's have a look. For example, I am giving you a formula C3H6O. Okay, so this is the molecular formula given. Now, what you have to do is you have to think what possible aldehydes you can make out of it, and then what possible ketones you can make out of it. Remember, ketone is RCOR dash and aldehyde is RC double bond OH. Now, can you go ahead and try to make an aldehyde containing 3 carbon atoms? So to save time, I'm just trying to go over quickly here. Of course, if you come to know the answer, just type it in the Zoom chat if you know the name. Can you tell me the name of the isomer which is aldehyde containing C3H6O? So 3 carbon aldehyde. So 3 carbon aldehyde means I can make like this, correct? So this is the display formula I'm using. So what is the name of this compound? This is the display formula. I can write this as CH3CH2CHO. So this is called propanol, correct? And you might also remember the SKF. So if I draw the SKF, it is going to look like this. This is the SKF, correct? So this is the SKF, this is the display formula, and this is the structure formula of propanol. Is there any other aldehyde you can make out of it? Is there any other possible, is there a possibility of a chain isomer? I cannot reduce the chain from 3 carbon to 2 carbon. I cannot do it. I can't do positional isomer because the aldehyde is terminal functional group. It is always carbon number 1. So I can only get one aldehyde out of it. Now try to figure out how many ketones can you get. A 3 carbon ketone. Can you try to give me the name? A 3 carbon ketone. At least you will make like this. You will make the ketone group here. This is the display formula, 3 carbon ketone. Now what is the name of this ketone? So this is a display formula, or I can write this as CH3COCH3. This is the structural formula, and of course the SKF looks like this. Now very quickly, what is the name of this compound? Very good. So this is propanol. Now is there anything I can do with the position of ketone? Can I remove it from second position? Now there is no second position. Remember, it's a 3 carbon ketone. The CO group has to be in the middle. Which means I cannot get any positional isomer, I cannot get any other chain isomer. So that is it. I'll get only one ketone and one aldehyde. So total 2 isomers I got. But in the isomers, you notice this one has the aldehyde group. That's the aldehyde group, and this one has the ketone group. So that is why this is called functional isomers. Have you understood? On a scale of 0 to 10, you are getting the idea how this works. Now, on the next page, I'm going to give you a little bigger one. These are all very popular questions in the exam. So let's have a look at another one, which is very, very popular. C4H8O. Okay, so once again, what I want you to do is, I want you to start working on, if you can get more than one aldehyde, please do it. If you can get more than one ketone, please do it. Okay, let me know when you're done. Try to make as many aldehydes and as many ketones as you can. As many aldehydes and as many ketones. So first of all, let's work with aldehyde. So how many aldehydes can you get? Are you getting one aldehyde or two aldehydes or three aldehydes? Can you tell me? Tell me 1, 2, 3. How many aldehydes are you getting? 1, 2 or 3? How many you can get? So there is this, okay, you can do a rough work. Okay, so I know this is an aldehyde, correct? Isn't that an aldehyde? Okay. So my first aldehyde would be CH3CH2CH2CHO. This is butanol, correct? Butanol, which can be 1, 2, 3, and this is the, okay. Is there any other aldehyde possible? Everybody could make only one aldehyde. Nobody could make two. I think two aldehyde is possible. I think 2-aldehyde is possible. You can make a chain isomer of this. You can make a chain isomer of the first one. Can you try, please? Try to figure out the name of this one. Very good, very good. So you can make a chain isomer, means instead of having chain of 4, you can make a chain of 3. So what you do is you make your 3 carbons like this. You make your aldehyde group and put 1 carbon here. So how will this look like? This will be CH3CH, bracket CH3 CHO. Did you all understand? Can you give me the name of this aldehyde? What is the name of this aldehyde? So this is carbon number 1, carbon number 2, carbon number 3. The SKF looks like this. That is the aldehyde at the first position, and that is the methyl group. What is the name of this aldehyde? This is 2-methyl propanol. Very good. 2-methyl propanol. 2-methyl propanol. So this is the second aldehyde. So we have two aldehydes there. These questions, they will come in paper 1, they will come in paper 2 also. So two aldehydes are possible with C4H8O. Okay, now do one thing. Let's try to work on ketones. Let's see how many ketones we can get. See, the formula still remains C4H8O. Can you try to figure out how many ketones? First of all, you will make a 4-carbon ketone. So what is a 4-carbon ketone? You will make 4 carbon like this, and you will put CO like this. Correct? Of course, you can write this as CH3, CO, CH2, CH3. What is the SKF? Second carbon, there is a CO. Now tell me the name of this compound. Very quickly, write in the Zoom chat. What is the name of this compound? It's a 4-carbon ketone. Now, remember the rule for ketone naming. The position of ketone group only is mentioned if there are 5 carbons. So this is to be simply called as butane-on. Butane-on. Don't say butane-2-on. Because 4 carbon, we cannot say position of butane. Okay, the ketone group. Now the thing is, do you think if I do like this, it is the same thing or a different compound? If I do like this, tell me, is it same or different? Like this and this, they are exactly same. Why they are same? Because here you are numbering from left to right, and here you are numbering from right to left. Did you get it? Give me yes or no. Correct. So that means I cannot get any more ketones. So total three isomers are there, 2 aldehydes are there, 1 ketone is there. Anyone has any problems? So what I said was, when you do functional isomerism, you should study them as pairs. That's usually the fastest way to learn. So this is one pair. The pair I'm talking about is aldehyde and ketone. So there is a switch between aldehydes and ketones. Now there is a second pair that you can work with. That also gives very good results. So this, let's have a look at. This is carboxylic acids and esters. And why am I taking them? Because they also have the same general formula. So this is my second pair. Now, do you remember the general formula of carboxylic acid and esters? You might remember CnH2nO2. Yes or no? Everyone remembers? So what you should understand is, carboxylic acid means it is C double bond O OH, correct? And ester means this is C double bond O and O. So everyone is okay with this. Now I'm going to give you I'm going to give you 2 molecular formulas, and you will make esters and you will make carboxylic acids. Make as many as you can, okay? So let's have a look at the example. So the first example I'm giving you is, I'm giving you C3H6O2. So this is the molecular formula. Now using this molecular formula, I want you to give me how many carboxylic acid can you get. Very quickly start. How many carboxylic acid you can get, and how many esters can you get. So first of all, you start with the carboxylic acid. Remember the naming of carboxylic acid, it's alkanoic acid. This is how we used to name carboxylic acid, alkanoic acid. And esters, we named them as alkyl alkanoid. All this we did in the previous sessions. When we started off with 13.1, I taught you all how to write the name, how to give the name and all that, and how to write the SF, how to do the SKF, all we did. Okay, come on. Everyone start now making carboxylic acid, 3 carbons. Let me know when you're ready. How many carboxylics you got? 1, 2 or 3? How many carboxylics? So I have 3 carbons. So this is the rough work you should always do. You can always use the display formula. You know it's going to look like this, correct? So which means my structure formula should look like CH3, CH2, COOH. The SKF 3 carbon. So carboxylic we write C double bond O and OH like this. And what is the name of this one? It's a 3 carbon, no? So what is the name? So this is propanoic acid. Now, is there any other carboxylic I can get? Yes or no? Can I get chain isomer? I can't make chain of 2 carbon. It still won't work. Guys, give me yes or no. Did anybody else get any other carboxylic? So only one I got. Okay. Now let's make some esters. So the trick is whenever you want to make esters very fast, you should always make the ester group first. Maybe you can make 2-3 esters and afterwards you can try to figure out how many will I get. So make an ester group first. Okay, so I'm making another ester group. Maybe I'll get so I have 3 carbons. Why don't you try and tell me how many esters you are getting? 1, 2, 3. Don't worry about the name. At least just try to guess how many you will get. So I have total 3 carbon, 1 carbon already finished. So I can put both my carbons like this and I can put H here. I can put 1 carbon here, 1 carbon here. But I cannot do like this. I cannot put both the carbons here because then I have to put H, it will become carboxylic, so I can't do that. So are we agreed that we are getting total of 2 esters? So which means I should get HCOO, CH2, CH3. Could you please go ahead and make the SKF also, because SKF of esters usually students make mistakes. So that is the, and this ester looks like CH3, COO, CH3. Okay, how do I make the SKF? Now when I make SKF, my C double bond O is the first carbon from the left hand side. So which means first carbon, that means that's the C double bond O, that's the O, and then first carbon, second carbon, see CH2, CH3, and that's the H we don't show. Okay, SKF of the first one. What's the SKF of this one? My second carbon is the C double bond O. So that means it should look like this. The second carbon is the C double bond O, and then there is oxygen, and there's one more carbon there. So that's the SKF of this one. Could you go ahead and give me the name of these esters? What's the name of the first ester? We cut the ester. We name it from the right side now. So this is ethyl. The first one is called ethyl, and here I can see only one carbon. So ethyl methane OH. Okay, done. What about this one? Second one. There's only one carbon on the right and 2 carbon on the left. So this is to be called as methyl ethanoate. Now slightly tougher question. See, this is C3H6O2. Slightly tougher question was C4H8O2. Let's have a look at that one also. It's slightly more tougher. C4H8O2. This is very good example. It has come many times in paper 1 and paper 2 for so many. In fact, paper 2 they have asked this independently for 4 marks also. C4H8O2. Okay, so now what I want you to do is I want you to make how many ever carboxylic you can, how many ever esters you can, and don't forget to make the SKF everywhere. So let's have a look at carboxylic first. You can type in the Zoom chat how many carboxylics do you think you will get. 4 carbon carboxylic. I'm looking at the Zoom chat on a different device. That's why you don't see on the screen. So just keep mentioning there. How many are you getting? 1, 2, 3, 4 carbon carboxylic. So the rough work should be, first you must make 4 carbon like this. See, this is the rough work. This immediately should tell you, okay, the first one should be like that. And then make the SKF. 1, 2, 3, 4. This is the carboxylic. And I'm sure you got it right. This is butaneoic acid. Now, is there any other carboxylic you got? This is the first one. Is there any other isomer you can make? You can think of chain isomer. Guys, could you just mention in the Zoom chat? Chain isomer, did you get it? How will you make a chain isomer of this? And try to give me the name of the compound if you can. How to give the name of that compound. So what you do is you make a chain of 3 carbons. So you know that's going to be carboxylic. So you put one carbon like this. So it will be CH3CH, CH3COOH. Carbon 1, carbon 2, carbon 3. So this is the name of this compound. You guys are not typing anything in the Zoom chat. It's very quiet. That's usually not a good thing. 2-methyl propanoic acid. Give me yes or no if you understood this compound. Okay. What about the SKF? Are you okay with the SKF? So 3 carbon, methyl is here. That's the carboxylic. So I could make 2 carboxylic acids only. Okay, now let's try to make some esters. How many esters you could manage? If you can give me the name of the ester, that will be fantastic. Like I have total 4 carbon. I think I did this question also before. Of 4 carbon, I gave you this formula and I had asked you to make 4 esters if you remember. Do you remember that earlier session? This question came in paper 2 exam also. C4H8O2, students were asked to draw 4 esters actually. So what you can do is the first ester, you can put 1 carbon here and you can put 2 carbon here. Okay, so this is 1, 2, the third carbon is the CO and then O, and what is the name of this one? This is methyl propanoate. The second isomer, what you can do is you have the ester group, right? So you can put 2 carbons here and 1 carbon here. So the structure formula SKF will look like this. And the name of this ester is ethyl ethanoate. So two esters, we got it. Then there is the third ester possible. I'm just trying to speed up, guys. This is the third ester possible. You can put all the 3 carbons here. Okay, so the SKF of this one is, so first carbon is the CO, okay, and then you have the oxygen, and then I have 3 more carbon. That's 1, 2, and 3. So this is propyl methanoate. Propyl methanoate. Now there is one more ester possible. So what you can do is this 3 carbon that you see on the right side, you can convert that into a chain situation. So what that means is you make 2 carbons and you stick 1 carbon like this. Okay, so this is another isomer. The naming of this Cambridge does not use. This is basically isopropyl. But let's have a look at the SKF. So the first carbon is the C double bond O, then O, then second, this carbon has the methyl group. So see, CH3, CH, and that's the CH3. Okay, so this is isopropyl methanoid. I'm just writing the name, but they will not ask like this because isopropyl, this is the isopropyl group, isopropyl methanoid. So total of, now how many total structural isomers we got for C4H8O2? Total 6 isomers we got. Sometimes it comes in MCQ also. You have to do this within 100 seconds. So 2 carboxylics we got, 4 esters we got. Okay, total 6 structural isomer we obtained from C4H8O2. Okay, give me yes or no. That is in terms of carboxylic acids and ester I'm talking about. Okay, on a scale of 0 to 10, tell me how comfortable you are right now. Everyone is okay? Okay. So let's have a look at now. So that's basically end of it. So we did structural isomerism, under which we did chain isomer, positional isomer, and functional isomer. There is another pair which I just want to introduce to you, officially not there, but we do talk about closed cyclic compounds. Okay, so I just want to take maybe a couple of minutes. I don't want to take any chances, but there is a switch which can happen between alkene and cycloalkane. Okay, so I'm just want to introduce this thing to you because alkene and cycloalkane, they also have the same CnH2n general formula. And alkenes, you know, is having CC double bond. Cycloalkanes, they don't have any double bond. Let me give you a very simple example. For example, if I give you C3H6, okay, C3H6, this I'm giving you, you may find this useful. So I can do CH3CH double bond. You know who this is? This is propene, correct? This is propene. And propene, this is the SKF. Everyone is okay? Give me Y for yes and for no. Propene, everyone is okay? So the isomer of propene is this. Now what I'm let me open it up. So this is CH2, CH2, CH2. So this is cyclopropane. Did you notice that the single double bond is gone? And do you notice the molecular formula is the same, C3H6? Give me yes or no. In alkenes, I see the double bond. In cyclopropane, there is no double bond. Functional isomerism examples these are actually. Okay, so that's cyclopropane, and you can simply write SKF of cyclopropane is like this. Just make the triangle there. I'll give another example. For example, we have C4H8. Now I'm making an alkene, okay? So everyone agrees. Can you very quickly give me the name of this alkene, which we write it as like this: 1, 2, 1, 2, 3, 4. What is the name of this alkene? You call this as but 1-ene, correct? Correct. The Zoom chat has to be a little active. I know some of you are busy today, but it's nice that you are still somehow be a part of it. So is there any other alkene I can make? Is there any other alkene I can make? Can I make a chain isomer? I can make a chain isomer. No, I can make a 3-carbon alkene, and I can put the methyl group like this. What is the name of this alkene now? If I do like this, what is the name of this alkene? So this is 2-methylpropene, correct? 2-methylpropene. Now I made 2 isomers of C4H8, and both isomers were alkene. Both isomers had CC double bond. Agreed? Okay. And what is the structure formula of this one? That is CH3, and then I have C, and in the bracket CH3 double bond CH2. Okay, so this is how we write the structure formula of this one. Now I want to make a cycloalkane out of it. So what I can do is I can simply make this. See, it is completely closed chain. The double bond is gone. Can you guess what is the name of this compound? What is the name of this compound? It is a 4-carbon cycloalkane. Because it is 4-carbon cycloalkane, I'm sure you understand it is called cyclobutane. Very good. This is called cyclobutane. Now in cyclobutane the double bond is not there. So you see so basically what I'm trying to tell you that this functional isomerism can happen between alkene and cycloalkane also. So there are 3 categories what you can consider: alkene, cycloalkanes, carboxylic acid and esters, and aldehydes and ketones. They can be considered. Okay, if everything is ready, we are now going towards the space isomerism. Any questions on structural isomerism? Everything is okay? Okay, let's have a look. So what we are doing now is space or stereoisomerism. So when we say space or stereoisomerism, so these isomers, they have same molecular formula. Not only molecular formula, they have same molecular and structural formula also. Now the structural formula also is same, but they differ in spatial arrangement. What that means is how the atoms are arranged in space. They are different there in spatial arrangement of atoms. Okay, in space. I mean, this is a very simplified way. So we are talking with respect to 3D, 3 dimension now. Okay, it's not 2 dimensions. Structural isomerism, everything is in terms of 2D, 2 dimensions. Space isomerism, everything is in terms of 3D, 3 dimension. Your notebook is 2 dimension. Okay, so whatever you write on the notebook, whatever arrangement you do, that's structural isomerism. Now what we are going to do, we are going to put some atoms above your notebook. We'll put some atoms below your notebook. We are going 3D now. That is space or stereoisomers. So there are 2 types what we have to study. The first one is called geometrical or cis-trans isomerism. So this is the first type what we have to study. And the second type is called optical isomerism. Okay, so we have to study how they are caused and how do we figure out the isomers and what's the difference between them. So first one is called geometrical isomerism, or sometimes also called as cis-trans isomerism. So if you're ready, we'll go to our next page. I'll wait for you. Is there any questions anyone has at this moment? I'm starting off with geometrical isomerism or cis-trans isomerism. Anyone has any questions for me? It's a short session today, but very quickly, please. You can use the mic. If you have no questions, could you please type NQ in the Zoom chat? Okay, so let's have a look at geometrical isomerism, also called as cis-trans isomerism. Now, when it comes to geometrical isomerism or cis-trans isomerism, there are a few points you have to keep in mind. Okay, the first point. Now, this is also with respect to AS level, because in senior classes there are some other possible angles explanation for geometrical isomerism, but here this is found in alkenes. That means So they have carbon-carbon double bond. Okay. So the second point, you have to understand something about the carbon-carbon double bond. So what do you remember about the carbon-carbon double bond? Now, do you remember that the carbon-carbon double bond is made up of one sigma and one pi? Do you remember this? Give me yes or no. Like, you are absolutely aware that in a double bond, there is one sigma and one pi. Give me Y for yes if everyone is okay with it. Single bond is sigma, double bond is one sigma, one pi. Everyone is clear with that. Okay. Now, keep in mind that when it comes to sigma bond, it is head-on overlap, correct? It is head-on overlap of orbitals. So that means SS overlap or SP overlap or PP overlap. So when orbitals overlap head-on, rotation about the carbon-carbon axis is allowed. Okay, so because of this, the way it's head-on overlap, right? So you can keep fix one orbital and you can rotate the other orbital without a problem. It will not break. Okay, if you just hold a pencil, two pencils together, hold one pencil and I can rotate the other pencil. This is sigma bond. There is no bond is not going to get broken. But when it comes to pi bond, there is a problem. If you remember, pi bond is by sideways overlap. Remember this. Sideways overlap of p orbitals. Give me yes or no if you remember this. Which is perpendicular to internuclear axis. Perpendicular to internuclear axis. Do you remember this? You studied this in the chapter of bonding. So that means the pi bond, if you remember, there was a p orbital like this and there was another p orbital like this. I know they will come like this, sideways overlap. So when they overlap, how do we make the pi bond? Remember, we used to make it like this. This is the orbital representation of a pi bond. So pi bond, as you see, it is spread top and down. Okay, the problem with pi bond is the orbitals are like this now. Okay, sideways overlap. So there is overlap on the top happening and there's overlap at the bottom right. So that means now the issue is I can't fix one orbital and rotate the other one. I can't do that. My rotation is restricted. That's the problem. Imagine if you're holding two pencils together. Imagine you're holding two pencils and if there was a rubber band here and a rubber band here. Okay, two sets of rubber band, one here, one here. Now if I want to hold the black pencil and rotate the red pencil, you understand I can rotate or you think I cannot rotate? Because there is a rubber band here, rubber band down. So if I want to rotate my red pencil like this, I can't rotate. Do you understand? Please give me yes or no. Like give me on a scale of 1 to 10. There is overlap on the top, there is overlap down. Because of that, orbitals cannot rotate around the carbon-carbon axis. Give me yes or no if you understand. So the presence of pi bonds causes restriction of rotation. So this is why the geometrical isomerism happened. It causes restriction of rotation of orbitals about the carbon-carbon axis. So around the carbon-carbon axis, the orbitals cannot rotate. Like I cannot keep this orbital fixed and I cannot rotate this one, like this. I cannot. That's not allowed. And because of this, now I'm going to write a very important statement. So the positions of atoms becomes fixed in space about the CC double bond. Now see what I'm trying to say? Because there is no rotation possible, the atoms around the double bond, their position in space becomes fixed. I can't rotate them anymore. So the way they become fixed gives rise to cis isomer and trans isomer. So now on the next page I will show you how they look like. So please understand the problem of this isomer. Why is it being caused? Because of the double bond. So what is the issue with the double bond? Because double bond, pi bond does not allow rotation. So what happens because it does not allow rotation? So because it does not allow rotation, the atoms around the CC double bond, their position in space becomes fixed. Because of this fixation of atoms around the CC double bond, this gives rise to geometrical isomerism. Okay, so let's have a look. Let's understand how do I represent this. So for example, now before I get into that, I'm going to write something which is very, very useful for you. Let's see conditions for geometrical isomerism. So if you isomerism, conditions for geometrical isomerism. So if you want to first of all check whether the compound will show geometrical isomer or not, you should immediately check these conditions. So there are two conditions. First conditions, obviously there should be CC double bond, presence of carbon-carbon double bond. This is absolutely required. Second condition is the presence of two different atoms or groups on carbon of carbon-carbon double bond. So let me explain. Don't worry. I know some of you might be like, what the heck this is. Let me explain what this means. It means if I give you a situation like this, okay, think of this as case 1. Okay, think of this as case 1. If I give you something like this, A, B, A, B, you tell me, will this compound show geometrical isomerism? Yes or no? Type Y for yes, N for no. Look at the two conditions. It has a CC double bond. Look at this carbon. Look at this. Look at this. They are different. Guys, give me yes or no. They are different, right? Look at this carbon. Look at this and look at this. They are different, same or different? They are different. It means this compound will show geometrical isomerism. Everyone agreed? Everyone agreed? No? Okay. Have a look at case number 2. What if I give you like this? A, B, A, A. Now what? Give me yes or no. You have to look at both the carbons connected by the double bond. Look at these two carbons. Look at this carbon, look at this carbon. Carbon on the left, is that carbon on the left okay? Carbon on the left, it has A and it has B. Okay, so they are different, I know. So that is good. So this carbon is okay. This carbon is not okay. Did you understand why? Because both are same. So this compound cannot show geometrical. Have you understood? Scale of 1 to 10. 10 understood, 1 you don't know what I'm talking. Everyone, scale of 1 to 10. Case 3. What about this case? Will it happen? Yes or no? Will this compound, case 3, can this show geometrical isomerism? I'm still waiting for your answer. You have to look at both the carbons. This carbon has A and B. They are different. So this carbon is okay. This carbon has C and D. They are both different. That means this carbon is okay. So that means this compound can show geometrical isomerism. Have you understood first of all? I'm going to give you a question and you try to apply this. Is that fine? Can I go to my next page? Just do one or two simple examples and we'll do more when I see you again. Let me explain how this works. So how this works very quickly is any carbon with CH2, it will not show. If there's a carbon like with anything which is identical, it will not show. Any carbon with a C double bond O, it cannot show. The moment you see a carbon with a double bond, it's not possible. Carbon with double bond oxygen, carbon with two hydrogens, carbon with two chlorine, any of these carbons cannot be involved in geometrical isomers. So this was the introduction. So when I see you again, I'm going to finish geometrical isomerism and I'll finish optical isomerism also.